Question 5. So we have reached rate of reaction now. So we're looking at how to monitor this reaction. This question is a bit tricky because they say something about inert solvent. So we are not using water, they are just using inert solvent. They represent it as SOLV in a bracket. So inert means unreactive, it doesn't react with your reactant or whatsoever. What can we see here? We have N2O5 in the solvent going to 2NO2 in the solvent plus half O2 as a gas. How can you monitor this reaction? That's the question. How can you monitor this reaction from the given information? The thing is, usually we will be looking at NO2, which is a gas. So usually it's a gas and it's a brown gas. But here it is dissolved in the solution. They say based on this information, so I would say to monitor the rate, I'll probably collect the volume of gas here. This seems to be more legit, but it's just me. And looking at the questions, they do say measurements. If you think about the plural, why do they give us plural? Because rate is the change in amount over change in time. So we got to monitor not only the change in amount, but the change in time as well. So in terms of the two things we need the volume. We can monitor the volume of O2 gas produced over a fixed time at regular intervals. So intervals meaning time intervals, and they are not asking us for the apparatus, but this is what you would use. You will use a stopwatch, and then to monitor the volume of gas produced, you will collect the gas. You can use a gas syringe in order to collect the gas, a stopwatch to monitor the time. So the change in the volume of gas produced over the change in time is going to give us the rate of reaction. They did say measurements, plural, so I'm giving two things that we need to record. It's a suggestive question. I'm not entirely sure if this NO2 will be colored in solution or not. Not a solution, sorry, in the solvent, because they don't say it's in water. The fact that we know it's a brown gas does not mean it's necessarily the same color in this particular solvent. That's why I don't want to go onto that route. Rather, I focus on what I can do better, which is to collect the gas. Part B, so question B, they are asking us, they give us a graph of how the N2O5 changes with time. So B part 1 is explain half-life. So these are basic definition. What I mean is you gotta be ready for this kind of definition. So it's the time taken for the initial concentration of a reactant to fall to half its initial concentrations, to half. Okay, so it's the time taken for that initial concentration to go to half its value, or to just half, HALVE there. Now determine the half-life of this reaction. Show you're working on the graph. What I'm going to do is I'm going to have to copy the graph and then paste it here. So otherwise, it's impossible for me to actually do it without doing the graph. I hope that will be alright. If that's not alright, then I'll just re-edit this video and take out the whole graph again if I'm being told that they'll violate whatever copyright thing again. Okay, so just give me a minute. I'll stop this video, and when I come back, then the graph will be here. Okay, I'm back, and this graph has magically appeared because I just copied it from the question paper. Okay, hopefully it'll be alright. Now they say show you're working on your graph. If they want you to show you're working on your graph, you gotta have a line. And I started with 0.25 mole per dm cube, which means when I half it, so 0.25 divided by 2, I get 0.125. 0.125 is somewhere there, so that is 0.125 mole per dm cube. So if I do it like that, then I will get somewhere in between there. So to read that carefully, there's 100, there's 200, so there's 120, 140, so there's 150 second there. You can't really do half-life just by the first one, but let's do a second one just to confirm what we are thinking. 0.125 divided by 2, I get 0.0625. This is 0.05. there. 0.06 is the next one, so I want 0.0625, give or take somewhere around there. Some people will say, oh, it's not very exact. Oh well, tough luck, it's just a graph. Then you have 250, 267, there's 280, so between 280 and 300 is going to be 290 seconds there. So as you can see, the first half-life there is 150 second. The second half-life between 150 second to 290 second, give or take, there is around 140 second. But again, I haven't been super exact, so I'm just trying to estimate a little bit here. I would say the half-life is pretty much constant there, pretty much confirming that it is first order with respect to N2O5. What do they want us to do? In part 2, they just want us to determine the half-life. I can just do the first one, which is just the green color one. So that is going to be 150 second. Always have a unit of the time based on the graph itself. On to the next one. So part 3, what is the effect on the half-life if the initial concentration is half? Well, if I look at that question is basically a repeat of what I have just said. I have said that, the second half-life, oops, I really don't want to do that. Perhaps I just go to the next page. Part B3 is asking you if the initial concentration is half. So that means we start from here. What is going to be your half-life? Your half-life is going to be, when you halve this again, it's going to be from here to here. It's about the same. So I can see that, this suggests the effect. So did they tell us it's first order? They did tell us it is first order. In the question, if you look carefully, just above part 1, the reaction is first order with respect to N2O5. So that means constant half-life. There is a given for first order reaction. Now they ask you to suggest what happened when you halve the concentration of that. There will be no change at all. So half-life remains the same, or it remains constant, because we know already in the question they already told us that it is first order with respect to N2O5 back on page 10, just above part 1 question. Moving on, so C part 1, use your graph to determine the rate at 200 second. Very specific, at 200 second, we need to draw a tangent at 200 second. A tangent, because this is a curve, you cannot get gradient of a curve unless you know the equation, then you can do calculus. But given a graph like this without equations, the best thing I can do is draw a tangent. So let me just change the color. Not too sure how well this graph will be. No, that is not good enough. I want my tangent to be centered at 200 there. So what I can do is, let's play around with this. That is actually not good enough as well. So perhaps I can do this. That is probably better. So what you would do on your ruler is you extend this a little bit, like that. I can do it very easily on my screen, but it's probably a lot easier on your paper as well. But you move around until you have a tangent at t equal to 200 seconds based on the question. If I were you, I wouldn't be focused on reading other coordinates. This is 0, 0. This is a perfect triangle, so I might as well just read the y-axis and the x-axis. The y-axis there, it cut at 0.19, so it's 0.19 minus 0.00, meaning the change in y, 0.19 minus 0.00, divided by the change in x, so delta y over delta x, as you know, it's going to be gradient of the tangent. So that cut halfway in between 400 and 420, so there's around 410 seconds. On the x-axis, 410 minus 0. You have second on the x-axis, you have mole per dm cube, and there's no other thing given in the information there, so that is going to be my gradient, which I'm going to copy paste and put it here now. So just do that on your calculator. You get 0.19 over 410. 0.19 divided by 410. They don't tell us how many significant figure, but let me look at the question. If you look at the data given, these are 1 and 2 decimal place, or you can think about 1 and 2 significant figure. So I think what is appropriate number of significant figure is going to be 2 significant figure. So 4.634 times 10 to the minus 4. That is purposely done in order to, before I run up, so that I just want 2 significant figure. I look at the next one. So 4.6 times 10 to the minus 4. Do not forget unit. Out of good habit, you should always have unit in your answer. 2 significant figure was chosen based on the data given in the table. The concentration N2O5 was given to 2 significant figure. To the next part of the question, C part 2. Use your answer to C part 1 as well as this red equation. So red equal to K N2O5 to the power 1 first order. I want the red constant, so K equal to the rate over the N2O5. If I have at 200 second, this is my rate at 200 second. What is my concentration of N2O5 at 200 second? The concentration of N2O5 at 200 seconds, reading from your graph, at 200 seconds, so this is the point there, at 200 seconds, the concentration N2O5 is 0.10 mole per dm cubed. So 0.10 mole per dm cubed. I have my expression there, so I will just move it down there and go up there. So now I am ready to put in everything. So 4.6 times 10 to the minus 4 mole per dm cubed per second. They say use the answer to the previous bit, which I'm doing, and then I have 0.10 mole per dm cubed. The mole per dm cubed and mole per dm cubed will cancel, therefore giving you a unit of second minus 1. That will be 4.6 times 10 to the minus 3 second minus 1. They do want you to give the units for the red constant as well. Last but not least, don't have much space down there. Perhaps I can finish this without writing a lot. So we're looking at another equation. So rate equal to K, NO2, NO3. I think I better move on to the new page because I think I can talk a little bit about this. And this basically means first order. And this is first order. And it's with respect to that particular reactant, with respect to that particular reactant. And we have these 2 NO2 plus O3 going to N2O5 plus O2. We know it's 2 steps. We are asked to write down 2 equations, 2-step mechanism. So what's going to happen is, in the slow step will be whatever that appear in the red equation is going to be in the slow step. So there is 1 time NO2 in the slow step and 1 time O3 in the slow step in the red determining step. That's the meaning of red equation. That's the meaning of red determining step. One of them is involved in the slow step. Overall equation, there are 2 of them. So perhaps what I can do is I can set NO2 plus O3. That will give me, and if I have O2 as well, then the O3 become O2. That means this become NO3 maybe, something like that. And what happened then is the NO3 will react with another NO2, and I'll get NO3 will react with another N2. So another NO2 will react with another this NO3, which come from these and these. That will give you N2O5. When you look at the equations, 2 of these plus 1 of these and these will cancel out because they are intermediate in this reaction, and they give you 1 of these and 1 of that. So this is consistent with the overall equation, and of course this is now a 2-step mechanism, and I can tell you the first step is going to be what you call red determining step. It's the slow step because 1 of these and 1 of these, as stated in the red equation, 1 of these and 1 of these affect the overall rate of reaction because they appear in the slower step of the reaction. This is a possible 2-step mechanism. Okay, and this can't be your first step because this has to come from somewhere. This is your intermediate, which you produce from the first step, and then you get your final product after you reacted the intermediate with another 1 of these NO2. Okay, so that's the end of this 9-mark question on rate of reaction.